Hi, this is Katsuaki Tanabe, Kyoto University. First of all, I'd like to thank the organizers of this conference for providing us the opportunity to present our recent results. In this presentation, I'd like to share a plasmonic concept for condensed matter fusion. The intensity and density of the triggering energy supplied to activate the nuclear fusion reaction are key factors to produce a smooth and reproducible initiation of the reaction. The incident electric power onto palladium samples in liquid and gas phase systems reported in the field of condensed matter nuclear fusion has been generally around 1 watt per square centimeter or less. On the other hand, semiconductor or solid-state lasers are able to strike power densities several orders of magnitude greater. This approach aims an initial local ignition of nuclear fusion reaction, enabling the generated heat there to trigger subsequent reactions throughout the field material. Free electrons in metals, particularly around metal surfaces or interfaces with dielectric materials, exhibit a strong interaction with electromagnetic fields or light in the form of collective oscillation named surface plasmons. The electromagnetic field intensity around subwavelength size metal particles can be highly localized due to the coupling between the incident photons and collective oscillation of free electrons at the metal surface, resulting in focusing of electromagnetic energy density, or namely local field enhancement. Surface plasmon-induced electromagnetic field enhancement on metal surfaces has been utilized for various applications such as chemical and biomedical sensing, optoelectronic devices, and optical cloaking. To quantitatively discuss the plasmonic field enhancement effect, the field enhancement factors is defined as the ratio of the electromagnetic field intensity around the metal object to that in the absence of the object or the original incident field. In this manner, the field enhancement factor represents how much energy can be concentrated from the incident optical or electric power. Based on the Maxwell's equations, we calculated the spatial electromagnetic field distribution around metallic objects in the quasi-static limit. The details of our calculation method are found in our papers. They are the calculation results for the field enhancement factors for spherical metal nanoparticles in deuterium and heavy water. Aluminum, silver, and gold show distinctively high enhancements because of their high electric conductivities. Palladium, nickel, and titanium show enhancement factors about 10 in this optical frequency regime. For metal nanoshells, the field enhancement effect becomes much stronger. For example, silver silica spherical nanoshells show peak enhancement factors as large as 1000, and we can tune the resonant wavelength or frequency by the core shell diameter ratio. We quantitatively showed the electromagnetic and optical energy enhancement effect on spherical metal nanoparticles and nanoshells, with peak enhancement factors about 1000 for noble metal nanoshells and about 10 for the transition metals commonly used in the community. Here, we calculated for spherical particles and shells for simplicity, but further enhancement is available by sharpened nanoparticles and nanogaps, as I will present later. Such a plasmonic boosting effect might have been unconsciously produced in the experiments reported so far in the community, particularly for the electrolysis-type ones with applied electric field. Next, we calculated the field enhancement factors on planar metal surfaces and sharp tips. As seen in these plots, surprisingly, we found for planar surfaces that large field enhancement factors over several hundreds are available for palladium, titanium, and nickel in the microwave regime, even surpassing the enhancement for noble metals. Conventionally, plasmonics has been discussed mainly for noble metals, and our result was actually a new finding for a wide range of hydrogen energy field. For sharp metal tips, depending on the aspect ratio of the virtual spheroidal structure, we observed very large enhancements or energy focusing effect like antenna. We believe that it is important to actively utilize such plasmonic field enhancement effects for the improvement of reaction rate and reproducibility, particularly in electrically or optically driven systems. Not only for the metal surface, but also for metal oxide interfaces contain surface plasmons. For planar interfaces of the common combinations of metals and oxides experimentally investigated in the community, we calculated the field enhancement factors. Then we found that a certain degree of field enhancement is attainable for palladium, nickel, and titanium. And basically, oxides with smaller dielectric constants exhibit larger field enhancement. Here are the results for spherical metal nanoparticles embedded in oxide materials. Local energy enhancement over 10 times is seen for a wide range of optical frequencies through visible to near infrared and beyond. Similar to the case of planar metal oxide interfaces, silver, aluminum, gold, and copper exhibit distinctively higher field enhancement factors than other metals due to their high conductivities. We can therefore take advantage of such high energy concentration, for instance by simply coating the conventional palladium-based fair materials with noble metal nanoparticles. It is also known that surface plasmons in between multiple metallic objects with nanoscale separation distances, or so-called gap plasmons, provide large field enhancement factors. Consideration of the gap plasmon effect for practical applications is important because nanogaps commonly exist in real structures such as rough metal surfaces and ensembles of metal particles. Therefore, we calculated the plasmonic field enhancement factors in metal nanogaps. On conditions of the separation, large field enhancement factors over 10,000 were observed. We found that the enhancement factors for the metal species commonly used in the community will compete with those for noble metals in the microwave regime. Again, we believe that it is important to account for such a gap plasmon effect because nanoscale gaps commonly exist, for example, on rough metal surfaces and in metal particle aggregates. For simplicity, we calculated for spherical particles, but combination of this gap plasmon effect with the previous nanoparticle nanoshell effect and the sharp tip lightning rod effect would provide further field enhancement. Our experiment. First, we annealed a palladium plate for the purpose of surface cleaning and to obtain a complete single crystal structure for reproducibility. And then we deposited a gold thin film onto one surface of the palladium plate as an electrode for electric bias application and a diffusion barrier for deuterium. Next, we let the palladium plate absorb deuterium. Finally, we applied electric field and optical power to the deuterium-loaded palladium plate. To produce the plasmonic energy focusing effect, we implemented noble metal nanoparticles on the surface of the palladium plate before the experiment. We spin-coated a colloidal solution of silver nanoparticles with proper surface pretreatment and drying procedures. In the SEM image, relatively high-density silver nanoparticles on the palladium surface are observed, and we can expect not only the plasmonic field enhancement effect on the planar palladium surface, but also the nanoparticle and nanogap effects. As the experimental result, we observed a sudden increase of the temperature of the palladium sample and also an emission of gas species of mass numbers of 3 and 4. The species of a mass number of 4 was identified as helium-4 as a shoulder peak on the deuterium peak. The species of a mass number of 3 could be helium-3 or HD. For the neutron detection results, we simultaneously detected neutron intensity peaks from 2 independent gas proportional neutron detectors at the coincident timing of the sudden temperature increase. Then we carried out energy spectrometry by using liquid scintillators with a great technical support by Professor Honda and Professor Kasagi of Tohoku University. The neutron count around 2.5 MeV at that specific timing was unfortunately not significantly larger than other time regions. This is the summary of my talk. For the plasmonic field enhancement effect, significant energy density enhancements are attainable for the deuterium-absorbing transition metals commonly used in the community. Importantly, this plasmonic field enhancement phenomenon is applicable for electrical bias voltage application as well as optical irradiation because electromagnetic field and optical photons are equivalent. This effect may have been unconsciously produced in the experiments reported so far. We believe that it is effective to take the plasmonic effect into account in the design and optimization of the experimental systems, including material species, structures, and operation conditions. Finally, I'd like to thank the funding agencies, my students, and collaborators. Thank you for listening.